All right, so this is the masterclass on chemical equilibrium, and we're going to get started straight away. Not there. We're going to get started straight away with the questions. All right, so the questions that were asked start over here. It says the reaction of methane gas, which is CH4, with steam, which is H2O gas, produces hydrogen gas. There's our hydrogen gas, and there's also carbon dioxide in here. It doesn't mention the carbon dioxide, but it's still there. You can see it in the reaction. Initially, 1 mole of methane and 2 moles of steam are sealed in a 5 decimeter cubed container. When the equilibrium is established at a certain temperature, they don't mind what the temperature is. They're just committing that it's a fixed temperature. So the Kc is the same. The value of the Kc is 0,018. That value of Kc is relatively small, and it tells us that relatively small amounts of our starting materials react to produce products. You are asked to calculate the equilibrium concentration of carbon dioxide. This is a 7-mark question, which says that it's mediumly difficult to relatively difficult. So what I'm going to do is I'm going to give you a quick head start. I'm going to stop sharing. I'm going to start setting up my own table, but I will check in on you. And if you have any questions, I'm going to please ask you to ask them. All right. So I'm going to pause share now, and I'm going to get started on my working out. All right. Is everybody good with this? Does everybody understand what's expected of them now? I assume all of you have an idea as to how to do Kc. Brilliant. Okay, fantastic. So let's get going now. Go for it. In case anyone's worrying, this one isn't a nice one. I'm struggling a little bit too. I think this question is going to test me to actually do the questions rather than just screen them. All right. So, ladies and gentlemen, before I go any further, I'm going to first of all ask who's managed to come up with a KC expression. We've got KC is equal to, and then all of the things in the square brackets with the powers. Okay, cool. Most of you should have been able to do that, even if you were then sitting there with your drawer on the floor going, I don't know what to plug in. Fantastic. That's a good start. Second thing, did everybody manage to set up your table with the initial number of moles for everything? Okay, good. Who can tell me what problem we hit after that? And it was a very quick problem. I found that the problem I hit after that is that I didn't know anything else. And it's a horrible place to be, because when you don't know anything else than that, you've got to start dealing with maths and maths variables. So I'm hoping that maybe one of you came up with a better solution, but I haven't seen anything here that allows me to do this without bringing in, someone said, in terms of X, and I haven't been able to do it without using X. I just quickly want to show you what I've got so far. Please, you can give me thumbs up when we get to each section, just so that I can have an idea. I'm going to make you guys a little bit smaller, otherwise I'm not going to be able to see my screen. But who here managed to, first of all, get that first row over there correct? All right. Good. By the looks of things, most of you got the first row. And who got the expression of mass action correct? Okay, some of you. Now, the thing with this expression of mass action where I find a lot of people make mistakes is people want to leave off water, okay? Because you spent so long being taught that if it's a liquid, you leave it off. But this isn't a liquid, this is a gas. So as soon as we have water in the form of steam, you do include it. Please, your rule isn't that water has a concentration of 1 or a value of 1. It's that a pure liquid or a solid does. So over here, I should have had hydrogen to the power of 4 from there, carbon dioxide to the power of 1, methane, and water to the power of 2. I haven't actually checked that my number of moles of everything balance. I'm getting caught out a lot here, but it looks like they do. All right. Okay, just give me a second. I got to go and check. Yes, somebody's right. I did make a mistake here. So I messed up in terms of my change here. I've got to go back and change it. Sorry, this is why I keep you guys around. Yay. So I then did my change, but I did mess up. That should be a 2 and that should be a 4. So I'm going to quickly run through it. You got to remember this is still fresh. So the initials are here. Then this change column, if you remember, is where we put everything in the correct mole ratio. So I am going to assume here that I use up X moles of methane. Therefore, I use up 2X moles of water. I make X moles of carbon dioxide, and I make 4X moles of hydrogen. If we start with 1 and we use X, we've got 1 minus X. If we start with 2 and we use negative 2X, we've got minus 2X. If we start with 0 and we make X, we've got just X. If we start with 0 and we make 4X, we've got 4X. Then to get from the number of moles to the concentration, we remember that concentration is number of moles over volume. So this is 1 minus X over 5. 2 minus 2X over 5, X over 5, 4X over 5. Okay, just remember that that over there is the end of the table. Over here, once you've done your expression of mass action or your Kc, technically this side is called the expression of mass action. And if it's equal to Kc, then we can assume we're in equilibrium. Believe it or not, by plugging in this value of Kc here, you got 1 mark. I just needed to correct it because there were a couple of things that I got wrong there. So that would become a 4X over 5. That would be that. That's correct. And then I've missed my 2 in there because I didn't actually do my mole ratio. There we go. All right. Now, can I ask just quickly, did anybody come up with anything that was different? Did I miss anything besides the mole ratio, which we just filled in? Did I miss anything that would have made this an easier method to do? Okay, I didn't think so. And unfortunately, it is horrible because it's now all down to maths. So what I'm going to end up with is I'm going to quickly do as much maths as I can and hopefully not mess it all up. So 4 to the power of 4 gives me 256. Then I'm going to have x to the 4 over, okay, in fact, I'm just going to multiply everything here if everyone's okay with that. Actually, maybe I won't. I'll be good. 5 to the power of 4 is 625, and that's going to be times by x over 5. I'm not jumping in there yet because I don't want to mess up too much on my maths. Here I'm going to have 1 minus x over 5. Here, if I neaten this up, I am going to have, now I should write this out twice that I don't mess up. I'm hoping I'm not going to. So I'd have 2 times 2 is 4. Then I'd have minus 4x and minus 4x again, which is minus 8x. And then I'd have plus 4x squared over 25. Okay, everybody good with this so far? Now, I'm going to just quickly ask if everyone can quickly take a screenshot of what they've got here. I just want to, I'm going to have to remove some of it because I don't have enough board. The question was calculate the equilibrium concentration of carbon dioxide. So please note that the concentration of carbon dioxide at equilibrium is going to be x over 5. Now, anyone who is worried about their maths or stressed or anything like that, I'm just going to remove all of that there. From here to the final answer is probably only 1 or 2 marks. There may be a mark for working out x, and there may be a mark for later doing the divide by 5 to get back to here. But the point is, the maths here, while it will take a while, isn't that impossible. So here I'm going to have 256x to the 5 over 625 times 5, 3125. Okay, then I'm going to tip in times because I actually want to bring this up to the top. So I'm going to have 5 times 25. I get 125 on the top. Bear in mind that's from those two. And then on the bottom, I'm going to have 1 minus x times by 4 minus 8x plus 4x squared. As I said, this is the nasty bit where the maths is actually what you're getting tested on. It's a little bit inconvenient. I ideally don't like it. Now, what I'm going to do is I'm going to try and get rid of as many numbers as I can. So I'm going to work out what happens with all of these terms. So 0.018 times by 3,125 divided by 256 divided by 125. I get an answer, I'm going to leave it that way, as 9 over 5120 is equal to x to the power of 5 over, and then I'm going to start working here. Now, I panic when I do these because I'm always worried that there's going to be a maths thing that I trip over and that I don't get it right because of. So I think here the maths is actually getting incredibly nasty. Okay, there may be another way, but I'm not seeing it at the moment. If anyone is seeing a simpler way, please do shout. Then that'll be minus 4x cubed. Whew. I don't know if this becomes easier. Okay, let's try and see if they're like terms. This is the point at which you're saying, I'm getting tested on, is this physics or maths? And the answer is it's actually maths. Okay, so those two will be minus 12x. Then we'll have plus 12x squared minus 4x to the 3 is 9 over 5120. Some of you are lucky enough to have the calculators that do all of the thinking for you and solve for functions. And I think, to be honest, that is the only way you're going to get this answer. Okay, so I'm cross multiplying here, that will equal 5120 x to the power of 5. I do not know if I messed up somewhere, if there was an easier way around of doing this, but it really doesn't feel like there was to me. Okay, so I'm in fact at this point going to pause on this question. You can by all means calculate to the final answer of x, and then once you get that value of x, plug it into here. But I think that this question quite a while ago stopped being about equilibrium constants and concentrations and became way more confusing. So can I ask just quickly, did anybody get any further than I did on this? Does anyone have smarter calculators? All right. Anyone? Okay, I'm going to take that. Is everybody okay with us just leaving this here and saying, you know what, we don't need to go any further? Yeah, your calculator said can't solve. So I think sometimes I'm very good at taking these with a pinch of salt and going, wow, I shouldn't pick an old question that I haven't checked the answer to. But can you all see how you would go about solving something like this? Please note, in an exam, if it gets this messed up, I'd usually recommend you just step back and you're like, it's okay, it's not my fault, I didn't do anything. We usually can expect you to work with x squareds and to factorize and to be able to do quadratics, okay? But we can't expect you to do anything. I don't think even cubics are usually there, because at that point, we're no longer testing your science, we're testing your maths, and that's not the focus of your exams, okay? So at that point, you can turn around and go, it's okay, I'll lose the last mark and keep my sanity. I do recommend if you finished your whole paper, you come back and try this one again. But I think with this particular paper, I cannot see where I've gone wrong. And I do definitely believe that this gave us a very big value, which is to the x to the 4. And from there, it goes downhill. All right. Okay, so I'm going to quickly clear this. I have a sneaky suspicion that the people who got this earlier, who said they hadn't solved it, had a very good reason for not having solved it. All right, so we're going to start on a couple of application questions, and then we'll move to specific examples. So these may be general calculus, but I think they're sorry, not calculus. My brain's on calculus. General equilibrium calculations, Casey calculations, and the Shakyas, but we'll hopefully see that they come together. All right, question 6.1. The following equilibrium takes place in a 500 centimeters cubed sealed container, and the equilibrium is established at 900 degrees Celsius. Okay, so over here we've got calcium carbonate solid, calcium oxide solid, and carbon dioxide. I think I came across a similar one that I did with you in the previous lesson, but I don't think it was this one. All right, so the first question asks you to state Le Chatelier's principle. I firmly believe that when it comes to doing past papers, every definition they ask you to state, you write out. A lot of people are lazy and they go, oh no, it's cool, I know it. Okay, the problem is you think you know it until you try and write it down, and then you realize it's actually a lot harder to write down than you think. So without looking, can I please ask all of you to quickly write down Le Chatelier's principle? All right, I'm going to quickly pause while you do that, and I'm going to see what you're busy doing. Okay, so busy looking at Le Chatelier's principle. Please give me a thumbs up when you're done with it. Okay, good. Good, good. Okay, now I'm hoping you're all writing this down without looking. I know it's really easy to write it down while you're looking, but with these, I want you to always practice writing it down without looking. Okay, I only saw about 7 thumbs up, so I'm assuming the rest of you maybe don't know it so well, but I'm going to jump back to it. So my version of Le Chatelier's principle, and please, I do recommend that you actually go and look up the proper one. I spent so long marking this one that I get the ideas confused sometimes in my head with the exact words. So the important thing that you should have is that when a disturbance is applied to a system that is in equilibrium, the system will act so as to counteract the disturbance and to reestablish a new equilibrium, or to reestablish an equilibrium. In the lesson that we had in Le Chatelier's principle, I indicated to you that where the marks are is that you've clearly got to indicate that there was a disturbance, that there was an equilibrium, that the equilibrium was disturbed, and that we reestablish a new equilibrium. That's your first mark. The second mark is for stating that the system opposes the disturbance or counteracts the disturbance. All right, so if you've got both of those points in, you've got your marks. All right, It is then found that the number of moles of carbon dioxide decreases when the container is cooled. So the number of moles of carbon dioxide over here decrease when the container is cooled. Now, I'm going to ask all of you to quickly try and write out an answer to 6.1.2. Is the forward reaction exothermic or endothermic? And use Le Chatelier's principle to explain the answer. Now, I cannot emphasize enough how important it is that you use the words favored, okay, or the word favored. Okay, so I'm going to give you just a few seconds, minutes. We'll see how long it takes to quickly try and write down an answer. I'm going to write down an answer while you're busy doing this. All right. Oh, I didn't share with you at all. There we go. There's what I'm sharing. There we go. I'm going to pause it again. All right, okay, I'm going to ask now. I haven't yet asked, so I'm going to ask now who's already done with that. Quickly give me a thumbs up. I did see one of you had a thumbs up when we began. All right, now, ladies and gentlemen, when it comes to marking these questions, things get marked very strictly. So I'm going to tell you how they get marked so that you can make sure that you get to a decent answer. All right, and so that you get all of your marks. So here is my answer to this 4-mark question. Now, I'd like to start off by asking who wrote down the forward reaction is endothermic, or you started your entire answer with the word endothermic. Please, can I ask who has written down that the forward reaction is endothermic, or begun with endothermic, or ended with therefore endothermic? Okay, now I've got some bad news. If you don't have that line, you've got 0 out of 4. Okay, doesn't matter what else you've written down. If you have not written down that the forward reaction is endothermic, according to the way exams were marked at the end of last year, if there is no answer at any point, or if you've written down the wrong answer, we don't mark anything else. Okay, it's a little bit of a harsh reality because a lot of people kind of got some of this right but missed the bits where they were going. And you had to be very clear here because we're talking about both forward and reverse reaction. So you've got to be very clear that it is the forward reaction which is endothermic. Usually we assume that if a thing starts off with endothermic and then underneath you do your explanation, that was your answer, so we do give it to you. Or if you finished off with therefore endothermic, we can kind of assume that the endothermic is the answer to is the forward reaction. But if you've just got the word endothermic somewhere in among a jumble of other words, that doesn't count. So the way that I tend to deal with these is I first of all start with a general statement. A decrease in temperature favors the exothermic reaction. 1 mark there. If the temperature goes down, the system wants to increase the temperature, therefore it favors the reaction which gives off heat. We usually do not give you a mark for the explanation involving the temperature and the heat and all the rest of that. It's usually a mark for a decrease in temperature favors the exothermic reaction. First mark. The second mark, in my view, is that a decrease in temperature favors the reverse reaction because the number of moles of carbon dioxide is decreased. So I want you to link decrease in temperature to exothermic and the decrease in temperature to reverse. So you need to link decrease in temperature exothermic, decrease in temperature reverse. That's your second. And I would say here that therefore the reverse reaction is exothermic is where I'd put this third mark. And therefore the forward reaction is endothermic would be my last mark. There is a small chance that because they specifically said Le Chatelier's principle, that they may have put in a mark for something like, according to Le Chatelier's principle, you'd write that on full, the disturbance is a decrease in temperature, therefore the system will act to increase the temperature. Very small chance. I would rather, though, put my money here on this being where the mark is awarded. So these 3 marks are definite. The last one is either here or possibly there. And if you want to make sure that you've got it, you could possibly put in both bits. All right. Does that make sense? Who got that question 100% correct? Fantastic. Well done. You guys are champions. All right. Brilliant. If you didn't get it, don't panic. There's more learning that you can do then. All right. Then the next question says, and I'm just going to quickly clear everything, so please take a screenshot if there's anything that you need. Okay, I'm going to quickly clear everything because we're going to look at the next question, next portion of the question. It says the following changes are now made to the equilibrium mixture at 900 degrees Celsius. Please check that 900 is the same as the original temperature, so it's just to the original. Please always just check that because there may have been an increase in temperature there that you miss. More calcium carbonate is added. How will this influence the number of moles of carbon dioxide in the equilibrium mixture? Write down only increases, decreases, or remains the same. So I'd like you to think carefully on that. You're going to pick one of those 3 answers. And then the next question says that calcium oxide is removed from the container. How will this influence the value of Kc for the reaction? Write down only increases, decreases, or remains the same. So can I ask you quickly, I'm going to ask you to pick 2 answers, one for 6.1.3 and one for 6.1.4, and then we're going to compare the 2. All right. Okay, give me a thumbs up when you've got that. Okay. Still less than half of you. I'm not certain if I've pitched this a little bit too high. I don't think it's a bit too high. I think it's just necessarily maybe taking a little bit longer. All right. So I'm not going to spend too much longer. I think that that's a fair amount of time. I definitely know that more than half of you have given me a thumbs up. So my answers to these for 6.1.3 is remains the same. Now, this may surprise many of you because you're sitting there going, oh, but you've increased. If we add more calcium carbonate, surely we've increased the concentration of calcium carbonate. God forbid I even wrote that down. There is a solid there. The thing that changes or that would disturb the equilibrium is if there's a square brackets. This is a solid. It's not going to work that way. So I'm just going to clear all of this away and remember that it's a solid, and a solid, changing the amount of solid that's there doesn't change the concentration because it's not aqueous and it's not dissolved in anywhere. So I never should actually have written that square brackets of calcium carbonate because there's a solid and we don't even discuss that. Okay, so my answer here should be remains the same because a solid doesn't impact equilibrium at all. The second question was calcium oxide is removed from the container. Now, I'm going to be honest here. There's something that I haven't quite emphasized enough in these lessons, and I'm going to emphasize it now for you. But there is only one factor that affects Kc. Kc only changes if the temperature changes. So I can save myself a huge amount of time where they go, what happens to Kc? And I go, cool, what happened to temperature? Oh, nothing, cool, it remains the same. And I do not look any further than that because that is as far as I need to look and I'll have a definite answer at that point. All right, so I'm going to quickly go to see everybody who got those two correct. Did anyone get both of them right? Okay, some of you. All right. The rest of you, please don't feel bad. Those are the questions that most people usually mess up on. And the reason is that most people, the second they see anything about the calcium oxide is removed, they go, oh my gosh, concentration goes down. Some people think that the reason that this doesn't impact is because it's a solid. That may be a part of it, but even if we'd remove the carbon dioxide from here, the Kc value won't change. Now, I need to just emphasize on this because there's a big problem that a lot of people have with what I've just said. And it's one of those things that will get to you when you're sitting in the middle of an exam and you suddenly start to second guess yourself and you go, wait, but if this one goes down, then that reaction goes that way. The forward reaction is favored. So this goes down and this goes up. And then you're sitting there going, wait, the Kc depends on the concentration in this case, actually of only carbon dioxide, and then you're starting to query whether carbon dioxide goes up or down, and you get yourself into a total state about it. I'm promising you right now, no change that you ever make to pressure or to concentration of any starting material or product will affect Kc. Yes, all of the concentrations may change. Okay, in this case, they wouldn't because there's only one of them that affects Kc. But what always happens is that they change in such a ratio that at the same temperature, you'll get the same value of Kc. Okay, I'm promising you that to the point where I want you to actually in an exam just trust and go, it's okay. There's been no change in temperature. I'm just going to trust that Kc doesn't change. The reason I'm warning you on this is that a lot of smart people will sit here and try to see how it should change. And you'll be able to, if you think hard enough, you'll be able to convince yourself that it does change. And you're always going to be wrong. Okay, so Kc will not change unless the temperature changes. Promising you right here and now, it will save you a lot of having to think and stress. And there are no exceptions. Yes, it gets messy, but there are no exceptions. Okay. All right, this is a question for 6.1.2. Why does a decrease in temperature favor the reverse reaction since the concentration decreases? Okay, quickly, I hope I haven't made a big mistake there. Let me just quickly go and see which one you're on. 6.1.2. Okay, so just quickly going back to this, I'm quickly answering a question for someone here. You were told, and I'm just going to quickly repeat what I said here. So there was something where we said that a decrease in temperature favors the reverse. So we're told that the number of moles of carbon dioxide go down. Okay, now this is not a case of Le Chatelier's principle where we're trying to remove the fact that it goes down. This isn't Le Chatelier's principle for us that this is the disturbance. The disturbance is not the carbon dioxide decreasing. The disturbance is the cooling of the container. It's the fact that the carbon dioxide goes down tells us that it is being used up. If the carbon dioxide is being used up, it is because the calcium carbonate is being made. So you need to realize with this question over here that the disturbance is the cooling of the container and the decrease in temperature. It isn't that the number of moles of carbon dioxide decrease. So the disturbance is not a decrease in concentration of carbon dioxide, it's that the temperature is cooled. The decrease in carbon dioxide tells us that the response to the temperature decreasing is that the reverse reaction is favored. Does that make sense? So it's, and I can understand where you're getting your confusion from, but it's, you've got to realize that the reverse reaction being favored is due to the temperature, because in this case, the reverse reaction is exothermic, which means that the forward reaction is endothermic. All right. Sorry, I just quickly want to double check that I did manage to make better sense of that. All right. I think it's one of those little nitty gritty. Sometimes when you have two ideas in your head and you're quite certain that both of them are right, they conflict, and then you get a bit frustrated with them. So please, if you do have any of those where you've missed just a little bit, it makes it a lot easier to just ask. All right. Question 6.2 says the following reaction takes place in a sealed 2 decimeter cubed container at 450 degrees. The pressure is now increased. Pressure increased, that's our disturbance, by decreasing the volume. So if we have a smaller volume, all of our particles, instead of being in that much space, I'm going to quickly see if I can do this and do it well. All of the particles, instead of being in that much space, are in that much space. Can you see how we've effectively increased the number of particles per unit volume? So instead of them being there, they're all squished together. Okay. The question says, how will this affect each of the following? Once again, your only options are increase, decrease, or remain the same. And we're going to look at how will it affect the concentration as well as the equilibrium. When we talk about the equilibrium position, if the forward reaction is favored, we say it shifts to the right. And remember, if the reverse reaction is favored, we say that the equilibrium position shifts to the left. All right, so can I please ask you, what does it do to the concentration of HI at equilibrium and the equilibrium position? I'm going to quickly pause while you write in your answers or while you think about them. I think I'm going to catch you out on some of you out on this. All right. Can I ask an interesting question? Okay, this isn't for who's done it, so don't put up your hands yet. Who's got the same answer for both of the questions? Bad news, you're wrong. Got the same answer for both of the questions, you are wrong. You have fallen into the mistake pit they're expecting you to fall into. So I want to just quickly ask you to reread the line which says the pressure is now increased by decreasing the volume. And then think again about your answer. Okay. All right. Sorry, I know I had to ruin that for you. It's just that I'll give you a chance to correct yourself on what's most likely to be the mistake that most people make here. All right. Now that I put a spanner in the works for some of you, can I quickly check who's ready for me to tell them the answer? It's less than half of you, but I think I'm going to go anyway. Right, now it's half of you. Good. Okay, so my answers are the following. First of all, I'm going to explain my logic and then you can read my answers and check. But I said that there are 2 moles of gas starting materials and 2 moles of gas in the product. So the instinctive response for most people is that the change to the concentration of HI at equilibrium, there's no effect because the equilibrium isn't going to be changed. And that's 100% correct. The equilibrium position, there's no effect to it. Neither the forward or the reverse reaction is favored. And in fact, we'd even say that the equilibrium is not disturbed. However, the concentration of HI will increase because we're in a smaller volume. So concentration is number of moles over volume. And even though the number of moles remained the same because neither the forward nor the reverse reaction were favored, the volume here has decreased, which means that the concentration increases. Having said that, the concentration of hydrogen would increase and iodine and hydrogen iodide. All three of them would have an increase. And your equilibrium position, because we've got an equal number of moles of gas on both sides, there's no effect. Please, these only apply because there are an equal number of moles on both sides. If that wasn't the case, then both of those are likely to have different answers. Although it gets a bit tricky with the concentration of hydrogen iodide, because if the reverse reaction was favored, you might be tempted to say that the concentration decreases, but the decrease in volume may actually make the concentration still increase. So it gets a little bit tricky if you've ever got two things that contradict each other like that. All right, can I quickly ask who got both of those right? Anyone? Well done. Well done, well done, well done. You guys got the sneaky ones. So please just be aware of the fact that they often like to catch people out on how does concentration change because the volume has changed. It doesn't come up often, but probably every 5 to 6 exam papers, they throw in something sneaky like that. All right. Okay, can I ask everyone to quickly take a screenshot? We've got about 6 minutes left, so I'd like to quickly move on to one more question. Okay. Oh, and there's the one more question. All right. So we have got a question here. Sorry, I'm just checking I haven't skipped anything. There we go. So, oh, why is it skipping up? Sorry, I'm on as part of something here and it's not allowing me to move down very slowly. Okay, I'm just not going to touch anything for a while. I'm going to make sure that I go into my drawing pens first. Okay, hopefully everybody can see the new question now clearly. It says the reaction rate versus time graph below shows a change made to the equilibrium mixture at T0. And your question is to specify the change that was made at T0. Now, in the earlier lesson that we had, there was quite a large amount of discussion about what factors affect what in terms of temperature, pressure, concentration changes. All right, so I'm going to open this up to everybody right now, and I want to just quickly ask you, does anyone have any idea what the disturbance is? Anyone?
Maybe an increase in the concentration of reactants.
Good. That is the correct answer. So I'd say here, and it's a bit unfortunate because this doesn't actually have a label of which is your reactants and which is your products. Okay, so we don't know whether which one's forward and which one's reverse. But this here clearly indicates an increase in the concentration. Does that make sense? Ideally in an exam, and unfortunately the ones that I picked here, I think that there are bits of them that are missing. But if I told you that this here was the forward reaction, then you could say that there's an increase in the concentration of reactants. Please note, if I instead told you that this was the reverse reaction, then it would be an increase in concentration of products. So when we get an increase in temperature or pressure, both reaction rates go up quickly together. So they both go up together like this. When there's a change in concentration, one goes up and then the other gradually joins it. So there isn't a rapid change in terms of rates, because what's effectively happening is as you have more, now I think what was our reaction here? I think we had H2 plus I2 going to 2HI in that order. If we've increased the concentration of these, either one of these or both of these, it'll favor the forward reaction, which will produce more hydrogen iodide. As we produce more hydrogen iodide, there's more hydrogen iodide to reverse backwards or to react the reverse reaction and to produce our starting materials. So that's why that reaction follows, but there's a bit of a time lag to when it happens. And it's only as the forward reaction produces more product that the reverse reaction rate also picks up, because there's not more product now, which is its starting material to reverse backwards. All right, so the change that was made here was an increase in concentration. Hopefully in your exam, you know which rate was which, because it's actually impossible for you to tell from this, but there'd usually be a key down the side to make it a little bit easier. All right, hopefully that makes sense to everybody. Then we have a Kc calculation that's a little bit of a nasty one. Okay, so it says the following temperature and Kc values for the above reaction are given. So we're given the equilibrium constant at 450 degrees, and then we're not told what it is at the slightly higher temperature of 500 degrees. So you are told that a certain amount of hydrogen and iodine were pumped into a sealed 2 decimeter cubed container. At 400 Kelvin, when chemical equilibrium is established, it was found that there were 4 moles of hydrogen and 6 moles of iodine present. First question, which hopefully should go relatively quickly for you, is to calculate the concentration of HI present in the container at 450 degrees Kelvin. This should not take very long, so I'm going to quickly pause and give you a chance to do it. Before I pause, I'm going to be nice, and I'm going to remind you that the equation was H2 plus I2 goes to give you in equilibrium 2HI. Okay. All right, can I just quickly check who's got an answer? Good, good, good. Probably the more appropriate question is who's got an answer of 6? There is the working out as to how you'd solve it. So you had to bear in mind that you'd been given the Kc value of 6, you'd been given the number of moles of 4 and 6, you'd been given the volume of 2, and you knew that that was squared, so that'll give you a 2, a 3, 36, square root of 36 gives you 6. All right, so I think quickly just one more question. Who got that right? Okay, good, a few of you. And then last question for today that I'd like to just quickly do with you. It's the last one that I'd actually planned to do, so I'm getting pretty good at pacing us here. Says when the temperature was increased to 500 Kelvin and a new chemical equilibrium was established, it was found that there were 10 moles of HI present in the container, and you're asked to calculate the value of Y, which is the new Kc value. Now, I'm going to do something that's a little bit odd here. I'm actually going to use all of the equilibrium or all of the concentrations that we've got from here, the 3, the 2, and the 6, as my initial. And I'm going to do something even stranger here, because we're not going to start with 0. We're going to start from where the reaction is. Some people with this really like to go right back to the beginning, but it's way too much work. So I'm going to assume that my concentration initial, I'm starting with a concentration, not a number of moles. So my initial concentration of hydrogen iodide here is 6. Okay. My concentration, where are we, of hydrogen gas is 4 divided by 2 is 2. And my concentration of iodine is 3. Then I'm going to deal with the change in concentration and the concentration at equilibrium. I know it's a little bit of a weird way to handle this, but I'm just going to show it to you as an alternative so you don't have to go back to work out what we started with right at the beginning. You can just jump in here. So then you are told that it was, temperature, it was found that there were 10 moles of HI present in the container at equilibrium. So if it's 10 moles, divided by 2 decimeters cubed, that's 5 moles per decimeter cubed. So that becomes 5. If we start with 6 and we finish with 5, if anyone finds any errors, shout. But I believe that we've gone down by 1. We're doing all of our changes in concentration. We're allowed to do that because the volume is constant. So we're just assuming that we ignore all volumes here because they're all just going to cancel each other out. All right. So over here, we got 5, we got -1. This is in a ratio of 1 to 1 to 2. So this is going to be adding a half and adding a half. Okay. Please just be aware that you are allowed to do this because you're assuming here that your volume remains constant. All right, so here if you've got 2, you add a half, you get to 2.5. You've got 3, you add a half, you get to 3.5, and we finish on 5. And we're looking for our new value of Kc. We've already determined the expression over there. So it's going to be the concentration. I don't even need to rewrite this if I'm feeling lazy, which will be 2 squared over 2.5 multiplied by 3.5. From there, we get 25 divided by 2.5 divided by 3.5. And my Kc value is 2,86. Unless I've messed up on the maths, but I think the maths is okay. All right, so that's just a very unusual way that you can save yourself time. Because I think the problem with this is a lot of people instead try to go back to what the initial was over here. And then it gets very, very complicated. All right, is there a question? All right,
Yes, ma'am.
Yes, what is your question?
I got lost. I don't
All
understand how. I don't understand the question. I don't understand the answer, ma'am. Can you please explain again?
Okay, so this question only.
Yes, ma'am.
Okay, so what I'm doing here is we often will set this up with the number of moles initial, number of moles change, number of moles in equilibrium, and then we finish right at the end by working out the concentration in equilibrium, at equilibrium, okay? But because in the previous question, I worked out the concentration of HI and I worked out the concentration of H2 and I2. Because I worked out all of those, I can view this as being what was in the container when we were at 450 Kelvin. If I then increase the temperature to 500 Kelvin, I can assume that I'm going from here, which is my 450 degree Kelvin starting point, to this point, which is my 500 Kelvin equilibrium. So I do a table that's very similar to what you've done in the past. It's just a little bit different. So I had worked out here. I'm just going to quickly mute you if you don't mind until I'm done with explaining because there's quite a lot of background noise. Okay. And then I'll give you a chance to ask again just now. Okay, cool. There we go. So over here, I then went and worked out that this was the original concentration. 4 divided by 2 is 2, and 6 divided by 2 is 3, and that value is 6. They told us that it was found that at equilibrium there were 10 moles of hydrogen iodide. So instead of doing all of my calculation in number of moles, I did everything in terms of concentration. If I jump to concentration from the beginning, I'm allowed to work with it the whole way through. It's one of those things you're allowed to do. Okay, so instead of getting to concentrations right at the end, I spoke about concentrations en route. Please note the only reason that you may do this is that your volume remains constant. Okay, it's a little bit of a sneaky thing to do, and I know I've at points actually fought against it being done, but it's the easiest way to solve this, and I can promise you that it does work and it does give you the right answer. Okay, so what I ended up doing here was I worked through with all of these values. I said that I've got 6 here, I've got those here, and then they told us we had 10. So I said 10 divided by 2 gives me 5. So my concentration ends up being 5. Now you are not used to seeing situations where your equilibrium concentration of a product is lower than what you started with. So this actually tells us that by us increasing the temperature, we actually favored the reverse reaction because our hydrogen iodide is used, which is why it's minus, and the hydrogen and the iodine are made, which is why they've got pluses in front of them. So if I start with 6 moles per decimeter cubed and I finish with 5 moles per decimeter cubed, I must have, in this particular case, used up 1 mole per decimeter cubed. The change column here is always the one that's in a fixed ratio, which is 1 part to 1 part to 2 parts. So if we've got 2 parts being that we use 1, here we must use 1 to make a half and to make a half of a mole per decimeter cubed. Here we started with 2, we made a half, so we finished with 2.5. Here we started with 3, we made a half, so we finished with 3.5. And this one we've already worked out. This is already in concentration because we've done the whole calculation in concentrations instead of in moles. So at the end, I don't have to divide by my volume. Everything has already been divided by my volume right at the beginning. I'm then going to take it and I'm going to plug it into the equation. So I'm going to have 5 squared there. Remember, that's your concentration of Hi squared. That's divided by the concentration of hydrogen, divided by the concentration of iodine, which gives you a value of 2.86, and this is a Kc, so it's unitless. What we found here is that an increase in temperature favors the reverse reaction, which in fact could tell us in this particular case, if an increase in temperature favors the reverse reaction, increase in temperature favors the endothermic reaction. So that tells us that the reverse reaction is endothermic and the forward is exo. They didn't ask that, so we can just think it in our head and smile and move on. All right, can I just double check that I managed to answer your question?
Yes, ma'am. Thank you.
Okay, pleasure. All right, ladies and gentlemen, please take a screenshot if you need to of this question. This is a bit of an unusual one working in the concentrations, and it's just important that you remember that you can do this, but you can only do it if the volume remains constant. And at the end of the day, when you bring these in, that's where the squaring and funny things with the volume happen. So it happens after we've divided by the volume. So it's all good. All right, I'm going to stop sharing now. Okay, can I quickly double check who managed to learn quite a lot in terms of what we did today? Wonderful. All right, ladies and gentlemen, I hope to see you all again next week, Wednesday. I'm quite keen to make the official time slot the slightly earlier one. So can I just double check at this point, is there anyone who can't do a masterclass if it's from 4:30 until 5:30? Okay. So I think for next week, the masterclass is going to be from 4:30 till 5:30. Remember, you've still got to earn your way into it, but I am starting to find that I have very, well, a large component of the same people week on week. Okay, one person can't. All right. And we're going to have to see. We're going to have to see whether everybody's in here. All right. So I may juggle between the slightly earlier and slightly later times. I guess it'll depend on who's in the class. All right. Sorry, I'll be nice. I think it's very important that anyone who earns their place gets a chance, which is why today we in fact had 2 classes, because I felt a bit bad that people who'd worked so hard to get in couldn't attend. All right. So ladies and gentlemen, please get started on acids and bases. I hope that you're still enjoying the lessons and enjoying the master classes and everything else. I know that it's quite a juggle with the amount of schoolwork that you've all got. but I think that there's a huge benefit to practicing, and hopefully it makes it an easy environment in which to practice and learn. All right. Have an absolutely wonderful evening, everybody, and I shall hopefully see you all again next week, Wednesday. But before then, I'll hopefully see you tomorrow night with acids and bases, where we're going over pH calculations. All right. Cheerio. Bye-bye.